Welcome to lesson 1 of 4 in this tutorial, covering the topic of electromagnetism. This is the first video in our series of 4 lessons covering the topic of magnetism. Here are the key learning objectives for today's lesson. First, we will look at electric currents and magnetic fields, then at solenoids, drawing magnetic field patterns, and finally at interpreting electromagnetic diagrams. Here are the AQA Specification Points for today's lesson. Feel free to pause the video now and have a quick read through them before we begin. First, we will look at the strength of a magnetic field. Current can flow through a wire. As we've seen earlier, this is also known as the flow of charged particles. This current flowing through the wire is able to produce a magnetic field. The shape of the magnetic field is like a cylinder, with the wire in the middle and lots of circles going around it. The magnetic field strength around a current-carrying wire will vary. The closer you are to a wire, the stronger the magnetic field. We can see this in the picture here. Again, the closer the field lines are, the stronger the magnetic field. If we know the direction of the magnetic field around a current-carrying wire, we can find out the direction of current flow through the wire. We can do this using something called the right-hand grip rule. Simply make a thumbs up sign with your right hand. Curl your fingers, which will be the direction of the field, and the way that your thumb points will be the direction of the current in the wire. Look carefully at any diagrams you are given in exam questions, as they may give small details, such as arrows to show the direction of current or even the direction of the wire. Now let's look at solenoids and magnetic effects. A solenoid is simply a piece of wire that has been shaped into a coil, as shown in the diagram. Like other wires, they are able to carry current, which means that they can also produce magnetic fields. Since the wire has been shaped into a coil, each individual loop will have a magnetic field around it. All of these magnetic fields will be parallel to the solenoid's axis and all face in the same direction. This leads to an overall magnetic field that is both uniform and strong. Solenoids consist of lots of small magnetic fields which are close together. We already know that the closer the field lines are, the stronger the magnetic field will be. This means that the magnetic field around a solenoid will be stronger than the magnetic field around a straight wire. A solenoid is essentially the same as a straight wire, apart from the fact that it has been curled up. You may be asked to give a definition of it in an exam. Now we will cover the magnetic field of a solenoid. We've discussed that the magnetic field of a solenoid is parallel to the solenoid's axis, facing one direction. Outside the solenoid, we can see a very similar pattern to that of a bar magnet. Iron cores can increase the field strength. These are induced magnets, which mean that they become magnetic very easily in the presence of a current. When placed inside the solenoid, it will increase the magnetic field strength. However, when the current is switched off, the iron will lose its magnetism very quickly. An electromagnet is essentially what we've described on the last slide, a solenoid with a core of iron in the middle. A soft iron core is used in an electromagnet, and the coils of wire will go around it. This means we can switch the magnetism of the iron core on or off depending on whether a current is flowing. AQA exam questions tend to ask about the structure of electromagnets. It is important that you know an electromagnet is made of a solenoid with an iron core, and that you can switch it on or off. Next, we'll look at demonstrating the magnetic effect of a current. As we've seen in this section, currents through wires can produce magnetic fields and therefore have magnetic effects. The shape of the wire can affect the field strength. Solenoids have a stronger field compared to normal wires due to their curled shape. We can demonstrate the magnetic fields of currents. It's much easier to demonstrate the effects of currents in electromagnets. These can be switched on or off by switching the current on or off. Now we'll look at drawing a magnetic field pattern. For a straight wire, we first need to know whether the wire is going into the page or coming out of the page. If the wire is going into the page, it will be represented by a circle with a cross. If the wire is coming out of the page, it is represented by a circle with a dot. A good way to remember these symbols is to think of a dart. If a dart was coming towards you, you'd see the point. And if the dart was going away from you, you'd see a cross. Once we know the direction of the wire, we can use our right-hand grip rule to work out the direction of the magnetic field. For a wire coming out of the page, the fields will run in an anti-clockwise direction. For a wire going into the page, the field lines will run in a clockwise direction. There is a different shape of field for the inside and the outside of a solenoid. Inside, the field lines will run parallel to the solenoid's axis. Outside, the lines are going to be very similar to those of a bar magnet. To work out the direction of the field lines, we can use our right-hand grip rule as normal. Finally, we will look at interpreting diagrams of electromagnetic devices. We can represent these electromagnetic devices as diagrams. These are often represented as circuit diagrams. For exams, we need to be able to interpret these diagrams. They are often of simple electromagnetic devices, as shown here. This diagram represents an electronically controlled bell. The electromagnet is in the centre of the circuit. When the switch is pressed, it completes the circuit, sending a current through the wires. This in turn will switch on the electromagnet, causing the bell to ring. These kinds of questions are more to test your application of knowledge, rather than simply memorising different techniques. We've now completed all the specification points for today's lesson. Feel free to skip back through the video and re-watch anything you feel unsure about. We've now completed Lesson 1.